Part D, Quicksort. D.1, Introduction to Quicksort. Yeah, so this time, that same question again, why we need to find a new sorting algorithm, this Quicksort. Yeah. So the one we just learned in the merge sort, the biggest reason we learned that one, it has very good worst case efficiency. Yeah, it can make its worst case efficiency big theta of n log n. That's the most important reason we choose merge sort. Yeah, but it does not mean it has the best average case efficiency. Yeah, actually, it does not have. So, and we want to find some new sorting algorithm with very fast average case efficiency. Yeah, so that's the reason we need to try to find a better sorting algorithm. Yeah, so let's look at now our new consideration. We want to emphasize overall performance. So the overall here corresponds to average case. Yeah, average case. All right, yeah. Okay, yeah. All right, so we have to change our view another time, this time. Although still divide and conquer, so you can see all these algorithm, insertion sort, merge sort. We use divide and conquer approach to understand. And here for this new one, Quicksort, we use the divide and conquer approach. The main difference is how do you do the divide step? How do you do the conquer step? Conquer step, the same, the recursion. Yeah. We use recursion to do the conquer step. Yeah. Nothing special. But how do you do the combine step? After you conquer, you need to combine the results of the subproblems. When you do divide step, you divide original problem into several subproblems, but you need to combine the results from those subproblems. So the combine step, we will see that. Later we will do a chart to see the main difference in divide step and combine step. Yeah. All right. So let's do our sorting problem another time. Yeah. Still using divide and conquer. Yeah. Our goal, make the overall performance as fast as possible. How to make overall performance fast? Yeah. All right. So let's look at the detail. Yeah. If you want to do that, you need to, tolerate poor worst case performance. Yeah. So for this new one, you may need to tolerate. Yeah. That means you cannot have the property of the merge sort. You can avoid poor worst case efficiency. You need to tolerate poor. How poor? How much poor do you mean here? That's big theta of n squared. This one we mean it's poor. Okay. Now, you may not be able to get a big theta of n log n for the worst case. Yeah. But why you can tolerate it, right? Because the percentage of for that worst case is very low, very, very low. Okay, yeah. So for that reason, we do not worry about it. So if we use this sorting algorithm many, many times, yeah, the chance we can get the worst case is very little. Okay, yeah. All right. The probability for the worst case is very low. Yeah. All right. Now, let's change our view on divide and conquer. Yeah. All right. So we need to bring back our merge sort, and we want to do comparison here. Yeah. So let's do the chart here. Yeah. You can see we compare merge sort and the new idea. Yeah, this new idea we refer to the quicksort. In these three steps: divide step, conquer step, combine step. The conquer step, we don't worry because both of them rely on recursion to do the conquer. Yeah. But divide step, quite different. For the merge sort, we split right in the middle. We do not need to do a lot of work, right? Yeah. So we do not need to do any comparison, right? Yeah. Although we may need to do a little work, yeah. But that little work is very little. So we can use this big theta of 1 to represent a little amount of work we need to do for the divide step of the merge sort. But combine step, we need to do a lot of work, right? The combine step, big theta of k. K, here we mean the data size, number of elements in our data we want to merge, the combine step. Now, we need to do a lot. So you can see the main work for the merge sort here, combine step. But for the new idea, new algorithm, yeah, we want to change this pattern. Yeah, we want to spend more time on divide step. Yes, divide step. Yeah, yeah. So here, you make your decision to distribute your work. Where do you want to distribute your work? Yeah. For this new one, we want to distribute our work mainly at the divide step. But for the combine step, we can enjoy the good property we derived from divide step. We enjoy the good property. That property would give us big theta of 1. Little amount of work to combine 2 ordered arrays. Yeah. It's impossible. Yeah. So if some of you may ask why we cannot just find a new sorting algorithm with very little amount of work in divide step and also very little amount of work in combine step. It's impossible. It's impossible. Okay. Yeah. Yeah, it's hard to explain why it's impossible. Yeah, because you have to do some meaningful work, right? You have to do some meaningful work. Yeah. If both big theta of 1, that means at both places you do very little work. So then your algorithm pretty much trivial. Okay, pretty much trivial. So how can you solve a relatively hard problem? Right? Yeah. So, yeah. All right. So let's look at the details of our new sorting algorithm. Yeah. All right. The quicksort. Yeah. All right. The question. Yeah, because at the combined step, we do very little amount of work. So we want to start from relatively easy step. That means the combine step is very easy. Yeah. So let's start with this easy step. How to make combine step easy. Yeah. So let's imagine in what scenario we can get a very easy combine step. Almost do nothing. Yeah, almost do nothing. That means easy, right? That means low cost. How can you imagine a situation that when we combine two ordered arrays, we almost do nothing? We do not need to do any special, manipulation. Yeah, almost nothing. What's that? So almost do nothing in the combine step. Can we describe a special data properties so that when we merge two ordered arrays, we do not need to do any comparison. We just put them together, then done, combined. Is that good? That is good, right? Yeah. Let me see Madison's question. If we know the max of one array is smaller, good. It means, yeah, you get the point. Madison, you get the point. The max of one array is smaller than the min of the other. That's exactly what we need. Okay. Now you can understand what is the reason we pay big theta of k at divide step. Okay. We pay this much. That's the cost we need to pay. Big theta of k at a divide step. All right. The reason is because we want to get a property on our data. What kind of property? Just like Madison, the comments of Madison, the max of one subarray is greater than, or smaller than the minimum of the other subarray. That property, this property is not free, right? This property is very important, very useful. So it's not free, okay? You have to pay certain amount of work or cost, certain amount of work to achieve that property, okay? To achieve that property, yeah? So that's the reason. So you cannot dream of this little pay, okay? If you only want to pay this little amount of work, big theta of one amount of work, you couldn't get that relatively big property, okay? Yeah. All right, so now you can understand, so, why we distribute our work in this way. All right, yeah. So now I use diagram to explain the relationship between these two subarrays. Yeah. Yeah. When we combine them, we do almost nothing. Yeah. All right. Okay. Yeah. But before, yeah, when we do combine operation, we do it after conquer, right? Yeah. Before conquer, each one is not sorted. Each one is not sorted. So you should not combine them, okay? So you need to conquer, you need to sort each subarray first. Then you can combine them, yeah. So before conquer, not sorted, okay? Yeah, but here we don't worry about the conquer step because we do recursion. Yeah, we do recursion so we can make it. Yeah, so we leave it to recursion, okay? Yeah. All right. Then, now we can imagine both subarrays are sorted. Now we want to combine them to get a bigger ordered array. But when we combine them, we don't want to do comparison. Yeah. Yeah. So the good thing is, if we have certain property, then we can combine them with, without any comparison. Okay, yeah. All right. So here the condition, condition basically just like Madison type it there. Yeah, but here I want to use a math formula to represent it. Okay, yeah. All right. So here we need to get that property. Yeah. That property, we should have it before conquer, right? Yeah. Because when we do conquer, we do not move elements around, right? Well, sorry, we do not move the elements cross the line. Okay, we do not move elements cross this dotted dashed line. Okay, you move elements within the subarray, and that's fine, no problem. But we never move elements from A to B, from B to A, cross that line. Okay, all right. That means the properties you should make sure your two subarrays already have that property before conquer. Yeah, before conquer, after the divide step, you should have that special property. Okay, yeah, all right. So the property is A of I. So the value of A subarray, anyone you can imagine the largest one, right? Yeah. Even you put the max element in A subarray, this inequality is correct. And the B subarray, B of J, we refer to any element in B subarray, right? You can replace it by the minimum of B subarray. It should be also correct. So here, this inequality gives us the maximum of A subarray should be less than or equal to the minimum of the B subarray. If you have that, if your divide step can help you achieve this property, then we can enjoy the great result of this property when we do the combine operation. Yeah. So the hard work is how can you get that property in the divide step? That's the critical part of this algorithm. If we get this critical step, then we're done, right? Then the whole sorting algorithm is there, yeah, is there, right? Yeah, because we just apply the recursion, we can get the whole array sorted. Okay, so here our main effort we need to put in that divide step. All right. So the most important step, divide step, for this new method. Requirement. Yeah, a requirement. How to split the array into two subarrays, A subarray and a B subarray, such that A of I less than or equal to B of J. Yeah. Okay. Yeah. Definitely, we do not require A subarray, B array are sorted at this point. Yeah. Not too much. Yeah. We do not need that. When we do the divide step, we do not. Yeah. So if A subarray is ordered, B subarray usually not, because we leave that part to the conquer step, to the recursion step. Yeah. All right. Yeah. So now the next step, now our main, the critical step, we call it partitioning in Quicksort. Yeah. That's the partitioning step, partition step. Okay. Yeah. We do partitioning. Yeah. That's the special partition. Okay. Yeah. So what's that? Yeah. So here you can see, yeah, this A max less than or equal to B min. Yeah. So that's, what the Madison told us. Yeah. All right. Implement the divide step, now the details. It's not easy. We need to do a lot of work. Yeah. This step is quite smart, actually. Very smart, the step. Yeah. All right. fixing the implementation details. Yeah. Let me use another diagram to convey the main idea. Yeah. All right. So when we start this is our data array. Okay. Yeah. How to split? Yeah. How to split? Yeah. At some point, right? Yeah. So first you need to split somewhere. Yeah. But that point, where to split, that's a hard question. That's a hard question. Okay. You need to do a lot of work. Yeah. All right. Yeah. So after the split, we want to have this property A of I less than or equal to B of J. The question, how can we get this inequality? Yeah. How can we get this inequality? Yeah. Yeah. Because it looks pretty hard, right? It looks pretty hard. Yeah. And we don't want to do too many comparisons. If we need to do too many comparisons, then this algorithm won't be very efficient. Yeah. All right. So here we need to deal with some kind of uncertainty, yeah, regarding the sizes of A subarray, B subarray. Yeah. Here we do not even know how long is A subarray and how long is B subarray. We don't know. We do not have that information. That's uncertain. Yeah. Yeah. When you determine that, okay, yeah. All right. How to make it certain in a simple way, yeah, in a relatively simple way. Yeah. So here, the trick, yeah, the key point, a special element to separate two subarrays. How do we separate these two subarrays? Yeah. We need to find a special element in the original array to help us separate these two subarrays. Yeah. Here you can see the role of that special element is very important here. The role. Yeah. Some element, yeah, we need to, we need to have some new concept of the special element. Yeah. All right. So the key property, yeah, that special element should have this property, in place property. Yeah. How can you make a special element to separate two subarrays such that A of I less than or equal to B of J? Yeah. So now you think in this way. If we have A of I less than or equal to B of J, then some special property in the middle to help us separate these two subarrays, that means this special element must be in place, right? Think about that. This special element must be in place. If it's not in place, then later you need to move this element, right? If it's in place, then you never need to move this element because it's already in place. You just leave it there until the end of the sorting. Okay? Yeah. You never need to touch it. Yeah. But if it's not in place, you need to move it, to its final location. Yeah. So here we require there is some special element. We need to make sure after the divide step, it is in place. Then at the left-hand side of this element, all smaller or equal to this in place element, its value, and the right-hand side elements, B subarray, all greater or equal to the value of the special element. Think about that scenario. Okay, that special arrangement. Think about that. That's very critical. This requirement is very critical. Yeah. So let's try to understand this part a little more. because only when after this special arrangement, then we can go to the next step. Yeah. All right. Determine the boundary of two subarrays. So that special element plays the role as the boundary of two subarrays. But we need to determine that boundary, right? Yeah. So that's important. Yeah. So in this diagram, I call that special element between A subarray and B subarray P. Yeah. And we give a special name called a pivot element, P. Okay? Yeah. So here a new concept is introduced. The pivot concept is introduced. Yeah. So in our device step, we need to determine our pivot element, and also we need to put it in place at the end of the device step. Put it in place. Then, and still in our device step, we need to make sure, the elements in A subarray should be at the left-hand side of the pivot, and the elements in the B subarray should at its right-hand side. That's the amount of work we need to do in the device step. If you can do that, then you complete the critical step. The remaining work, much simpler. So we don't worry, the remaining work, almost do nothing for the combined step, and the conquer just recursion. Yeah. So we get a whole sorting algorithm. Yeah. But let's look at the detail of this device step. Yeah. This time we introduce this P element. So then our property, this divide condition, this property is written into these two inequalities. We introduce a new element P, and we want to make sure A of I less than or equal to the P value, and the P value less than or equal to B of J. Why we make this kind of change, you will see here, you can see this P element is used as a reference, certain reference, special reference point. Yeah. What's that? Yeah. Because when you compare A element and the B element without reference, then it's hard to control, because there is no standard you can apply, right? Yeah. A moving bar, yeah, some bar is moving. Yeah. But here we want to fix our reference. This P, we choose it as a fixed reference. Then we want to make sure all the elements less than or equal to P, we put it in the left-hand side of the P. And all elements greater than P, we put at the right-hand side of the P. Then it's much easier, right? Because we have a fixed point, but P, we choose some P first. Yeah. How to choose P, you will see later. Yeah. How to choose P, P can be chosen randomly. Randomly. So we do not need to do anything, just use a random generator to pick a P. Okay? Yeah. So we pick P, but after we select that P, it is fixed. It is fixed. Its value is known, it's fixed. Then we go through the whole array. When we see any element less than or equal to P, we put it at the right-hand side of the P. The element that is greater than P, here, yeah, let me just use this, strictly greater than P, we put it at the right-hand side of the P. In that way, you can see the split step, not that hard, right? Not that hard. Yeah. Selecting P randomly, that's not hard. Then go through the whole array from left to right do comparison with P. Okay, each element we do comparison with P. If it's smaller, we put it in an A subarray portion, left portion. If it's greater, smaller or equal, if it's greater than P, we put it in the right subarray portion of the P. Yeah. So the idea, implementation, almost there, but still some technical work you need to fix, some technical work. Yeah. So let's try to address remaining technical details. Yeah. All right. Which element is used as the pivot? Any element has an equal role in the array. Yeah. Because given an array, you do not have any information regarding the values, right? Which element has what value, you have no idea on it. If you do not have any information related to the values in the array, then any element in the array should have equal chance to be that pivot, right? The probability is the same. That means no matter how you pick your pivot element, you get an equal probability to be a good one, okay? To be a good one. Also equal probability to be a bad one, okay? It could be a bad one, it could be a good one, okay? Yeah. All right. Yeah. The good one, bad one, yeah. So you can think about, so what is the good one? What is the bad one? Yeah. We will answer that question later. Yeah. All right. No reason to favor any particular element. Yeah. No reason. Yeah. Equally well, equally good. Yeah. No reason one is better than another. Yeah. Okay. Yeah. So then we just do random selection as the pivot. Yeah. All right. Yeah. All right. Yeah. But here when we say random selection, we mean mainly we talk about with respect to its value. Random. So random with respect to the value. Okay? Yeah. Why I want to emphasize this value thing? Yeah. Regarding the values, yeah. So we want the, random element when we consider its value. All right. But other than the value factor, there is another important factor, that is position factor. Each element in the array, there is a position, right? The first one, the second one, the middle one, the median, the last one, the positions are all different. So from the position-wise, they are quite different. The elements in different positions are quite different. So when we look at the positions, there are some good positions and there are some bad positions. That's different. So we should choose the best possible position to hold our pivot element. We cannot use a random position. Think about it. Yeah. Here, the value, we allow random value. Yeah. The value, the largest one, smallest one, median, anyone. So it's fine. We allow it, the random value for the pivot, but for the position, we don't want to select a random position for the pivot. Right? Yeah. Because for some special positions, you will do less work. For some positions, you need to do more work. Yeah. So you want to choose the most convenient position in the array. Most convenient position. So our next round analysis, we need to determine what are those most convenient positions we should use for the pivot element. Now, so let me use another diagram to explain this question. This time, we want to determine one special location to hold our pivot element. All right? Yeah. Think about somewhere. Yeah. So let's look at this red circle position. If we put it randomly anywhere in this array, yeah, this location, let's see what problem we may have if our pivot element is here. Okay, yeah. Now, because think about, we need to go through this element from left to right. When we see a new element, we need to compare it with the pivot, right? And determine which one should be at the left-hand side of P and which one should be at the right-hand side of P. We need to do this kind of comparisons, right? Yeah. All right. Because if you pick any locations here, first we know it's not in place in general. This element at the end of the device step, the pivot won't be in this location. Yeah. Most likely, we need to move this pivot element to its final right location. Yeah, that's one thing. Yeah. Another thing is, for other elements, when we move from left to right, right to left, this pivot element plays a role as the roadblock. Yeah, as a roadblock. We need to cross this boundary point, right? From left to right, right. We need to do a lot of work to manipulate left-hand side elements, right-hand side elements. So that's too much work. That's too much work. So we treat it as a roadblock. Okay? Block smooth flows from left to right, right to left. Yeah. Yeah. So we want to find those special locations in the array that won't block any other elements move. When we move other elements, those locations won't be a roadblock. Okay? Yeah. Think about those special positions. Won't block anything. Okay? Won't block anything. Yeah. So there are some special locations in this array. The first location in the array and the last location in the array won't block anything, right? Yeah. Look at these two special locations. Yeah. So when we move other elements around, left to right, right to left, we never need to touch these two locations, right? If we put our pivot element in one of these two locations, then for when we move other elements, very easy, yeah, yeah, moving around. We never need to touch this pivot element location, right? Yeah, they are at the ends. So that's good thing about the end locations. Yeah, endpoint locations. Yeah. So, but these two endpoint locations, we can pick anyone. Equally good. Yeah. The first one or the last one, just two different versions of the quicksort partitioning. Yeah. All right. All right. So here, yeah. So let's do our partition step using one of the two special locations. In our textbook, it uses the first location, and here in my notes, I use the last location. Okay, all right. Yeah. So let's assume we randomly select an element in the array and swap it to the last location in the array. One swap operation we can put there, right? Yeah. So after that swap operation, then we scan the remaining elements in the array from left to right and determine what elements should be at the left subarray and what elements should be at the right subarray. That's the implementation of our partition step. Okay, yeah. All right. So we imagine after we finish scanning this array, we will get this A left subarray and then B left right subarray in this way. Yeah. In this way. Yeah. Definitely satisfying the property A of I less than or equal to P and P, yeah, here, yeah, we can, strictly less than B of J. Yeah. All right. Yeah. Yeah. All right. Then D.3 implementation details of the partitioning step. Yeah. I like to run concrete example to show you the details. Yeah. Otherwise, we just use our imagination to abstract. Yeah. We cannot get a better understanding, yeah, in abstract way. We want some concrete way. Yeah. All right. So let's look at, yeah. Before I show you that example, let me start with straightforward implementation. Straightforward, because at the beginning to implement that partition step, it's not easy. Yeah. At the beginning, we feel not that easy. So we want to find some easy solution first. Then we improve it. Yeah. Because usually the easy solution may not be a good solution. Yeah. It may waste quite some resource. Yeah. It may waste some resource. Yeah. So then we improve it by reducing the part of the resource it wastes. Yeah. All right. So when we start, we use two auxiliary arrays. Yeah. Yeah. Because that will make our manipulation easier. Two auxiliary arrays. That's the resource. Yeah. Because when you use auxiliary arrays, that's the extra resource you use. You have some cost you need to pay for this part of the resource. Yeah. All right. So this is the original array after we locate the pivot element. Yeah. Then we scan the array, all the elements other than P from left to right, and we choose two destination auxiliary arrays. So these two subarrays are put here. That's two auxiliary arrays. And also the destination arrays for the divide step. Okay, yeah. Now, when we scan, it's pretty easy. So you scan from left to right, one by one in a for loop. When you have a new element, you compare it with P. If it's smaller, you just place it in the left subarray. If it's greater, you just put it in the right subarray. Is that simple? So simple. Yeah. Very easy. After you finish the scanning, then you have A subarray and a B subarray. But they are in two auxiliary arrays. So we need to copy these two auxiliary back to the original array. Yeah. So that's the reason we use them as auxiliary arrays. Extra storage locations, yeah, to make our implementation a little easier. Yeah. But after we finish this step, we can see the auxiliary array, this extra amount of storage space. If it's possible, we want to eliminate it. We don't want to waste this much storage space. Yeah. So we try to do the manipulation within the original array. That's our improvement goal. Yeah. So we want to get the same thing, left subarray, right subarray, but we do not want to use auxiliary arrays. That's too much resource. Yeah. So we want to reduce our resource consumption to the minimum. Yeah. So that's another important factor when you design an algorithm. You should control. Do not use too much computing resource, yeah, including the storage locations. Yeah. All right. Question. Yeah. So here we feel no, it should not too hard. It should not be too hard to eliminate these auxiliary arrays. It's doable. Yeah. But we should find a smart way to do it. Yeah. All right. Yeah. So next, we want to eliminate the auxiliary arrays with some very smart manipulation idea. Yeah. Okay. Okay. Yeah. So here, we need to control extra space used. Okay, to the minimum. You can use extra space, but we want to control to the minimum. Okay, yeah, all right. So let's look at the improved implementation here. Yeah, all right. Yeah, so we should do the manipulation within the original array. That means we need to manage all the locations in an organized way. We don't want to mess up, yeah, because if you do not keep track of the locations of these elements well, you may mess up. Okay, yeah. So here, in order to organize different parts of the locations, here I create several regions in the original array with different names. The first one I called S region. Why S region? Because S here means smaller than P, smaller or equal. Equal, we put it here. Yeah. So for all those elements that are smaller or equal to P, we put in S region. Okay, we put them in S region. S region, just the consecutive locations, we treat them as a block of consecutive locations. Okay, yeah. Another one, L region, L larger than or greater than, yeah. So, greater or larger than P. Okay, yeah. Strictly larger than P. Okay, the second region, L region, yeah, yeah. Then we also need to give a third region here. I call it U region, unprocessed, yeah, because some of the elements we haven't scanned, we haven't processed, so we leave them in that U region, yeah, for our discussion purpose. Okay, for our discussion purpose, yeah. All right. So we use 3 different regions to organize 3 different types of elements in the original array. So then when we do the manipulations, we need to move our elements around among these 3 different regions. Okay, so if we can make that kind of manipulation clearly, all right, keep track of different elements well, then we can complete this divide step in a clean way, okay? Not messy way, okay? All right, so let's look at that part, that detail part. All right, yeah. So A subarray corresponding to S region, B subarray corresponding to L region, and at the beginning, these two regions are empty, empty sets. Yeah, and we need to grow these two regions. At the beginning, unprocessed region, initially, the whole array except P. Yeah, we take that P out of these three regions. All right, but at the end, this U region must be empty. Yeah. That means we finish processing all the elements in that U region. Yeah. So then, after that, we have clear S region, L region, and remember our P should go in place. Our pivot element should go in place between S region and the L region as the last step. We need to place it in place between S region and the L region. Then we complete the whole divide step. Okay, all right. So after this description, next I want to use one example to show you the details, partitioning detail. Yeah, all right. So let me run this concrete example. It's a simple example. You know, I just run my animation. Yeah, I hope I use the remaining about 7 minutes to complete the animation of this example. All right, so this is the given array. Yeah. So first, we pick the last element as the pivot, yeah, because everyone randomly selected equally good. So here, yeah, I just picked the last one as the pivot element. Okay. Therefore, different regions, I use different colors to represent different regions. Yeah. The white color, that's for the unprocessed region, U region, okay? Yeah, white color. Yeah. Then S region, L region, I use two different colors. So you can see them clearly. You can see the boundary clearly. Yeah. All right. But we need to use extra space to swap some elements. Yeah. When we do manipulation, we need extra space to apply the swap operation to manipulate those elements, yeah, in different regions. Yeah. All right. Yeah. So let me run the animation in this lower part. Yeah. When we start, S region empty set, L region also empty set. Yeah. First comparison, compare the first element with pivot 4, 2 and 4. And we know 2 is smaller than 4, so it should be placed in the S region, and I use yellow color for the S region. So we grow S region from empty to one element set. Yeah. Second comparison, the second element compared with the pivot 8 and 4. 8 is greater than 4, so we place it in the L region. It's in green color, so we grow our L region from empty to one element set in this way. Okay? Yeah. So next, that's 7 and 4 greater than 4, so we place it in L region. Yeah. All right. Next one, compare 1 and 4. It's less than 4, so it should be in the S region. We grow S region containing 2 elements, But in the diagram, you see after we color element 1 to yellow color, 2 and 1, 2 yellow color elements, they are not in consecutive locations, right? Their locations are not in consecutive locations. That's not good. So we should change their locations to make all the yellow elements in consecutive locations. How to do that? How to make that change? We do swap operation. We do swap operation. All right? We swap element 8 and element 1. One swap operation, we can make the yellow region blocks all in consecutive locations, gray region elements all in consecutive locations. One swap. So you can see why the swap is useful in this partition step. Yeah. All right. So then let's look at the remaining steps. 3 and 4. 3 should be in the S region, yellow color, separated by that green color block. Another swap operation. 7 and 3 this time, we can recover to the desired structure. All right, the last one, 5. 5 is greater than 4, so we make it a green color. But the last step, we need to put the pivot element in place. How to put the pivot element in place as the boundary of 2 regions, yellow and the green blocks, another swap operation. Swap 4 and 8, another swap operation. All right. Yeah. After the swap operation, we complete the partition step. And you can see first, the pivot element is in place. Second, all the elements at the left-hand side of P is less than or equal to P, and all the elements at the right-hand side of P is greater or equal to, or not equal, strictly greater than P. That's the requirement we want to achieve in our divide step. Yeah. So with this example, you can see, yeah, we can make it. And without using the auxiliary arrays, we only use the minimum 1 extra location for the swap operation. Yeah, so we save a lot of resource. Okay, all right.